Thanks for attending today. Appreciate it. So, we'll discuss how we use nanobubble technology to increase recovery of natural resources. But to start, let me tell you a bit about our company, Moleaer. It's a Los Angeles-based company, about 6 years old now. It is proven technology. What we do is we manufacture what we call industrial scale nanobubble systems. They're used across a wide range of industries. We focus primarily on agriculture, aquaculture, oil and gas, and mining. And wastewater as well. We have over 2,200 systems deployed globally, over 50 countries. So although it is a new class of science, the company, which is really the pioneer of bringing this whole new category to market, has spent the better part of 6 years now really commercializing it and proving its viability. So a bit in terms of the mission, we focus on really helping industries utilize water more efficiently and to treat it more responsibly. When you look at how water is used, about 70% of the world's water goes to agriculture, about 20% goes to industry, and the balance obviously goes to you and I at home called municipal. Rather than focusing on how to reuse it and how to recycle water, we really focus on how to use less of it and how to increase productivity around all these agricultural industrial processes and how to also treat that water more responsibly, which really means reducing the use on chemicals like chlorine, herbicides, algicides, et cetera. And specifically in terms of how it relates to here, we really focus on increasing resource recovery. How do you think about where water is sort of the nexus of food and natural resources, within natural resources, oil and gas, mining, and as we merge into more of the hydrogen area, how do you utilize nanobubbles, which I'll touch on what they are in a minute, to increase the productivity of these different applications or industries? Within oil and gas, we're primarily focused on how do you stimulate oil wells using nanobubbles to increase recovery out of existing wells. In mining, although we look at a number of different metals, today our principal focus is on how do you increase recovery out of copper, through leach processes in heaps. And in hydrogen, a new area we're exploring, how do we improve the efficiency of green hydrogen process, basically the electrolysis process, by adding nanobubbles to the electrolyte. So a bit about nanobubbles. My assumption is the vast majority of you have probably never heard of this before. So when you're thinking about a bubble, you're thinking about gas being introduced into a liquid, a bubble forms, the bubble starts to rise. In industrial processes, you're trying to get that gas to dissolve before the bubble reaches the surface and pops. Nanobubbles do none of that. They are about 100 nanometers in size, so we call it 2,500 times smaller than a grain of salt. It's really about the size of a virus. And at that scale, you're really talking about a nanoparticle, not really a nanobubble. So we're forming gas particles that stay suspended in the body of water, that do not readily dissolve. So they do not float to the surface. You have a charged particle, you can now do something with it. And what we focus on as a company is what can you do with nanobubbles? How do you make nanobubbles and what can you do with them? So we look at these different properties and behaviors of nanobubbles. And we think about where they can create value or where they can enhance different types of physical, chemical, and biological reactions. Some of the unique characteristics of the bubble, they are hydrophobic in nature, which is highly relevant to our oil production applications. They have a charged surface. They're electrochemically active. They maintain that gas in that bubble and don't rise to the surface and pop and don't dissolve, so you can utilize that gas for different purposes. And the charge of the bubble also reduces the surface tension of the liquid. And all those different sort of behaviors or characteristics is how we think about what they can do in applications such as stimulating oil wells, extracting more metals from a heap, or even improving electrolysis processes to make hydrogen more efficient. So a bit about how our technology works. We did not invent nanobubbles. They've been studied about 20 or 30 years now. There are a number of different ways to produce them. Ours is a flow-through technology. Essentially what happens is we need some sort of liquid as the medium. So liquid is pumped through the nanobubble generator, which you can see here in that image. An external gas is introduced. We are gas agnostic. It could be air, oxygen, CO2, nitrogen, doesn't matter. We're also liquid agnostic. But for the principle of the conversation, in this case, we're putting air into water. And we do two distinct things. We dissolve a significant percent of that air very efficiently. And in the process of doing so, we form these 100 nanometer sized bubbles. Depending on the makeup of the water or the chemistry of the liquid, we'll produce bubbles in excess from anywhere from 100 million nano-sized bubbles per milliliter to over 1 billion nano-sized bubbles per milliliter. So an extraordinary concentration. And that gets higher and higher depending on the makeup of the water or what's in that liquid, so to speak. So the way we apply them in oil and gas and in mining for the purpose of increasing recovery is we focus on these three different types of benefits. We focus on surface tension reduction. Again, because of the charge of those bubbles, and depending on the concentration we're producing, we see reductions in surface tension. When you can start to reduce the surface tension of water, it flows through whatever it's flowing through more efficiently. So in agriculture, for example, when you add nanobubbles to irrigation, water flows through the soil more effectively. We believe there's a similar mode of action when you're injecting nanobubbles into a core, into a formation, the way the water will flow through that formation more effectively. That also improves the wettability of the liquid, so it's also going to enhance the penetration. And then we also look at the bubble's ability to scour. So the way we think about scouring, think of it as almost like a hard particle that is breaking apart whatever it's traveling across that's on the surface. We see that for things like biofilm reduction in food surfaces. We see that for scale reduction in pipelines. And we see that as a means for scouring oil off the formation as well as a means to improve the recovery of oil in this particular example. We focus primarily within both water floods and huff and puffs, and we start to do fracs as well. On the right side, you can see an image of the way our technology is applied. We bring a mobile system in. We are charging the water that gets pumped down hole with nitrogen nanobubbles. And at that point, we start to pump it down hole in sort of a huff and puff application, or if it's a water flood, we'll inject it continuously as the water is flowing back into the injection well after the oil water has been separated on the production side. A bit in terms of some of the results, we've done about 50 wells to date of various different types. Here's an example of the first ones we did, actually a much smaller, older field, very low oil cut, about 1%. The field was in Illinois. And in this particular case, we had 3 injector wells going into a formation with a number of different producers. And you can see over time in this continuous water flood, as we were adding more and more nitrogen nanobubbles into the formation, that we started to increase the total fluid production. And although the oil cut didn't change, the total fluid was increasing, and therefore the total amount of oil being recovered from the process increases as well. There's no additional use of chemistry here. There's no surfactants going in or viscosity reducers. This is strictly the addition of nitrogen nanobubbles getting injected into a continuous water flood. We see similar results across different types of applications within the oil recovery space, whether it's in a continuous water flood like this example, again like a huff and puff, and we're starting to move into more of the fracs and the frac and eventually hopefully into the refrac space as well. In our mining segment, where we primarily focus on copper, as I mentioned earlier, last year we announced a partnership with BASF. BASF is one of the leaders in providing specialty chemicals in the hydrometallurgy space for the purpose of increasing metal extraction out of heap leaching. The challenge in heap leaching is you create these enormous piles of rock after you've crushed the ore, and then you start leaching it primarily with sulfuric acid and other reagents or other basically chemical agents to be able to increase the recovery rate. As that ore degrades over time, the percent of the copper available diminishes with that, and the leach process becomes less and less efficient, although the actual total mining process becomes less and less efficient. The challenge when you want to leach or extract copper is you need a high oxidative state in that solution. Basically, you want to increase oxygen or use other oxidative chemicals. And you want to reduce surface tension, so you get the leach solution to penetrate the heap as efficiently as possible. The reason why we partner with BASF is that when you combine their specialty chemical called Lixtra, which is a surface tension reducer, and add oxygen nanobubbles, which maintains very high levels of oxygen in the solution for long periods of time, you get much greater penetration of this basically agent, this chemical agent known as the raffinate or sulfuric acid, going through that heap to try to ultimately extract more copper. But the results to date are actually significant. The percent increase we see through our column testing work, which we have now deployed into the field as well, shows substantial differences in terms of the copper recovery that you're able to achieve through leach processes when you combine the two solutions versus what you can combine with the control. And that again goes to the ability for these bubbles to maintain those very high levels of oxygen in the solution, combined with BASF specialty chemical to be able to get better penetration throughout the heap. The reason why that's so valuable is one of the long-term challenges related to not only the energy transformation, but also in terms of the cost to recover is the fact that there's going to be a supply-demand gap, as everyone's aware and talked about this week. And the ability to produce new mines fast enough is basically prohibitive. It's not going to be done possible. So we work with some of the largest mining companies, BHP and Freeport at the forefront of this, to find ways to increase that recovery rate through enhancing the leach process. In the middle there, you can see a picture of our nanobubble generator. It's the silver vertical line in the middle, on the middle picture on the left, going behind it up into a heap and essentially adding oxygen nanobubbles into that process. We also are looking at hydrogen closely. About 2 years ago, we experimented with a very small electrolyzer. What would happen if you put these electrochemically active nanobubbles, in this case we actually used air, it didn't matter what gas we were using, into the electrolyte to see if it increases the charge density of essentially the electrolyzer. And we saw some significant improvements depending on whether it was a PEM or an alkaline-based electrolyzer. And from those results, we filed some IP, so we have patent protection around the use of nanobubbles in the electrolyte for either hydrogen and also the chlorine electrolysis process, which is more commercially available today than the hydrogen side. And since then, we've gone on to partner with University of California, Irvine's National Fuel Cell Labs, and they've been doing basically sponsored research now for the past 9 months with 3 more months to go. And we are starting to look for partners, actively looking for partners in the hydrogen space to see how we can go from what we're learning in the lab to now to bring it out to become more commercially researched and ultimately see if it's commercially viable. But the goal here is very obvious, right? If we can increase the charge density of the electrolysis process, you can increase the amount of hydrogen producing without increasing your energy input to make hydrogen production more efficient. We see that same concept in other electrolysis processes as well. So it's not novel to hydrogen, it's novel to electrolysis as a whole. So just to sort of wrap up where we're at, this is, as I mentioned before, an emerging class of science, but it's growing exponentially. If you look at just research academic papers that are being published in the research community, and you look at what's happened in the last 12 months, over 2,000 papers were published last year alone. That's coming off about 10 years ago when you saw maybe 2 or 3 dozen. There's not a university I'm not aware of now that isn't looking at using nanobubbles in some application or another. That ranges from what Moleaer focuses on, around food production and natural resource recovery, all the way to healthcare, where it's being explored for cancer treatment. So it's certainly an emerging class that's growing rapidly. I think what Moleaer and a few other companies are showing is that it's also commercially viable. It's no longer just a technology that's being researched for research's sake, but also is something that is clearly demonstrating the ability to create value. And what we see here, again, is the opportunity to be able to help industries utilize water more efficiently. And if you can reduce the amount of water you need to increase to obtain the productivity you want, then all the other challenges related to water scarcity and water shortages go away. And obviously, given the nature of what we need going forward relates to food and availability of natural resources, water becomes a critical ingredient, maybe the cross-section for the sustainability of that to begin with. So, with that, thank you. Any questions?
Questions in or outside the pod? Any questions? Oh.
Please.
So,
Those behind
copper
you.
leaching.
Yeah.
In situ, have you looked at in situ copper?
We have not. It's come up with one of our partners for the future of copper mining. So we have never done anything specifically in an in situ process, but it's been on the radar for quite a bit with some of the large mining companies that we work with.
And your body's saturated in water, and you're dewatering that and driving a leach solution so that when you talk about
So
1%
Yeah.
sulfuric acid level,
yeah,
and it's going through the cracks in your body. So you're not actually moving any dirt.
correct. We are adding it directly into that solution, and then that ends up on the heap, and then it's penetrating through the heap.
We have no heat.
Yeah, but in situ, so it would be just going straight into in situ as opposed to into a heap. So from our perspective, and from the perspective of the 2 mines that have approached us on that idea, it should be applicable. No, Brad, have we spoken to them?
It's going into construction.
No. Okay.
Is that wonderful Italian red sauce?
Yeah. That's good to know.
So the other thing is, mining uses a lot of water, 4 tons of water per every ton of ore.
Yeah.
Can you mine water? So it's primarily
Yeah.
sulfates, like
Yep.
sulfates and sulfides carried from the metal, nitrates from the explosive material.
Yeah.
So can you move that from the water?
We can play a role. Have we done anything in that space yet? No. We've only been approached, right?
If you're super oxygenate the water.
Yeah.
You have more bubbles. That's what extracts things that are
Yeah.
fish hatchery and water. That's more like water.
The challenge we have, and it goes back to what you said, the amount of water that's used in mining makes our technology today cost prohibitive because of the sheer volume. So where it works economically on the front end because you're extracting copper, it's less interesting on the downstream, the tailings, for example, right? Because the money they want to invest there is obviously significantly less. So to date,
They invest in time.
because they have to. Yeah. Yeah. So we have not done that yet. Yeah.
Hydrogen. So the problem with hydrogen is it costs twice as much electricity
Right.
for the electrolysis process as the remaining power
Yeah.
in the hydrogen molecule. What impact is that ratio?
It depends if it's a PEMS versus an alkaline-based electrolysis process. But we have seen anywhere from just single-digit improvement to 25% improvement. The reason why we partnered with National Fuel Cell Labs, which happens to be an hour from our office at University of California, Irvine, is to focus on the optimization of that process and really understand what is the hydrogen increase for every kilowatt input that we can achieve when you add nanobubbles. But it's interesting when and it's coincidental that it comes to the mining side. The mining guys have worked with electrolysis for a very long time, right, from an electrowinning process. As soon as we mention the properties of nanobubbles, the first thing they ask is, have you used this in an electrolyzer yet? Because of the charge density change that the bubbles are going to create because of their electrochemical properties.
I'm going to get to that in the copper production.
Yeah.
There is the leaching.
Yeah.
Different process, the pregnancy solutions that have to
Yep. The other area in mining as well is froth flotation, which we have not looked at yet. And again, we're not going to flow anything out, but the bubbles are going to bond with the material, maybe enhance separation processes through the froth flotation process as a whole. But again, we haven't looked at it. Yeah. All on the radar.
I'm going to pass the microphone over here.
Thank you.
Hey, Randy Roberts, Chevron Tech Ventures. Maybe following up a little bit on chemistry applications. So for your oil and gas example, you showed that the total liquid production increased. But are you able to play around with the chemistry and the mobility ratios such that you would maximize oil production and minimize water production?
We have not been able to demonstrate that yet. And it doesn't mean that we can't. So for example, when you form a nanobubble, naturally air and water, for example, it's going to have a negative charge. We have recently figured out how to flip that charge to also have a positive charge if we want to. I don't know if that's going to play a role. My point is there's a lot to still be learning in terms of how the bubble interacts and creates that sort of mode of action for how the hydrocarbon comes out, and then to see if there's any ways to manipulate whether it's going to be preferential to the oil, preferential to the water, and also what is causing a greater total fluid production through the process as well. These are all sort of the big unknowns. It's interesting. We've done third-party research through one of the producers at universities. We've done third-party research through private labs, and then we've done field tests, and then also now we're just commercially just doing projects, not getting data from customers. But that's okay. Trying to bring that all together to understand mode of action is still a bit of a mystery because we don't really know what's happening. A 3-mile lateral, what's actually happening across the entire lateral to understand it. Yeah. And in the other area, we get some of the chemical companies that are involved in either EOR or improving frac performance, looking at nanobubbles as they call it more of like a carrier. So it's going to extend the life of their chemical, extend the effectiveness of their chemical. So it might also be that to be able to achieve something you're describing, may have to be a combination of solutions, not just nanobubbles on their own. Yeah. But certainly an area of interest. Thanks.
Thank you for the presentation. So, first question, are there any competitor companies that are working on the nanobubble technology? And if so, let's imagine I'm an investor and dealt with a couple of those companies already, and you're pitching your company. What makes your company stand out from the rest of them?
Sure. There are competitors emerging. I think the value that nanobubbles create and the size of the opportunities that we're in, it's inevitable that more and more competitors will come. That's okay, I guess. I can't speak to alternatives and also would never want to compare us to somebody else, but I can tell you what's novel about our technology. It is infinitely scalable, so we can scale to any flow rate. The smallest units we produce are lab scale units that are recirculating less than 10 gallons a minute. The largest one we have today is over 4,000 gallons a minute. It can go larger. It's versatile. It can treat almost any liquid with any gas. So we've had customers put CO2 into asphaltenes, literally pumping asphaltenes through it, trying to inject CO2 gas into it. And it's fairly cost effective. I don't think you'll find a lower, if you wanted to use a nanobubble metric, we produce the highest concentration of bubbles in the given volume of water at the lowest possible price. The real reason that I think Moleaer stands out is the R&D side. We have an R&D team that focuses really on two things. How do you make nanobubbles? What do you do with them? And I don't think there's any other company even close to that. And at this stage, we are surpassing universities in terms of that knowledge and understanding, and also correcting things that they have identified that are actually incorrect, which just speaks to the team. Yeah.
Out of curiosity, what is the lifetime of the nanobubbles? Like from point of generation, how far can you pipe this before you don't have any more nanobubbles?
So how far you can pipe it depends really on the nature of the liquids being formed into, like I'll explain water in a second, and then also, assuming there's nothing that's turbulent or disruptive in the process as a result. If you were doing like let me think of a 1,000-acre, nut orchard in California, nanobubbles will be at the last emitter on the dripper. We've tested that before. They will sit in the glass uncapped for weeks, if not months. But the variable that has the greatest significance is the nature of that water. If it's DI water, nanobubbles don't last very long at all. If it's a high saline water, they'll last for a very long time. If you go into a lipid-based chemistry that would be used in healthcare, you'd be into hundreds of billions of nanobubbles per milliliter, and they'll last indefinitely. So it's really a function of the other forces in that liquid that are playing a role in bubble stability and concentration.
So those ions in solution stabilize?
Yes, that's a big part of it. Yeah, we can dose a little bit of surfactant, and the bubble stability and concentration skyrockets. Yeah, it plays a big role. Yeah, yeah.
A question back here.
Hey, Nick. How do you choose which markets are the most attractive to go after?
Yeah, it's definitely one of our challenges. A bit now at this point in the company, it's about the adjacency to an existing market. So take mining, for example. We were introduced to the leaching, the heap leach business through a third party that was interested in utilizing the properties of nanobubbles to enhance heap leaching. Well, I never heard of heap leaching when that partner had reached out to us. So we figured, okay, so there's a credible company, they're willing to invest a lot of time and energy. At some point we say, oh, we've got this far enough along, now let's look at something like froth flotation, or let's look at tailings. We can't do it all. So a lot of it depends on whether it comes through a partner or it's something that is an adjacency to something we're already doing, like in the food space, which is our primary focus as a company before we started seeing interest from the oil and gas community, the mining community, and then the accidental hydrogen production result that we got in the lab, literally because of a crazy R&D kid on the team, which has been super interesting as a result. So, but it's one of the challenges because it almost feels like an infinite number of opportunities where these charged particles, which is essentially what we're producing, can create value. Yeah.
We still have some time for questions. Is there any more questions here in the pod or outside the pod? I have a quick question.
Please.
What, if you're looking at, you said you're agnostic on the gas and the water, is there a electricity demand that you have, and to what extent is that impacting your costs?
Yeah, that's a good question. So if you're if you're connecting our system to recirculate whatever liquid it is that you want to treat, there is a pumping cost. If we are utilizing existing pump, then we're basically not adding any additional energy other than the energy to introduce the gas, which is de minimis. So in like a frac project we've done, we just go on the discharge of the pump. In a huff and puff type application, we actually have to recirculate the water through our technology to get it to a certain concentration of nitrogen nanobubbles, and then it gets pumped down whole. And in mining, we've been on the discharge end of the pump as well. So it's highly dependent on the application and how it's being deployed. But there certainly can be an energy penalty, and there also can be an opportunity where it's essentially energy neutral, depending on the nature of the application.
Great, thanks. Any other questions? Okay, great. Thank you so much for introducing us to Nanobubble technology. If anyone has any additional questions, I'm sure Nick is happy to answer them.